Current observations of the night sky suggest that the physical elements of the cosmos, from the smallest planet to the largest star, are subject to the same finite limits as any other physical system. For 13.8 billion years, tracing back to the Big Bang, the universe has been in a constant state of expansion. Recent measurements indicate that this expansion is not slowing down as gravity pulls on matter, but is instead actively accelerating. Scientists attribute this outward pressure to dark energy, an invisible force that occupies the vacuum of space. To determine how the universe ends, researchers focus on the exact strength of dark energy. This is measured against the average density of matter, which generates gravitational pull. The balance between these forces dictates the future trajectory of expansion. By isolating these three variables, the final state of the universe becomes a matter of physical calculation. One mathematical outcome of these calculations is the Big Crunch. If the density of matter were high enough, gravitational pull would eventually overcome expansion, drawing all stars and galaxies back into a single, dense point. However, recorded outward acceleration shows the universe expanding too quickly for gravity to take hold, making a total collapse improbable. A second possibility is the Big Rip. This scenario assumes that dark energy will grow stronger over time, increasing its outward pressure. Space would eventually expand so rapidly that it overcomes the gravity holding galaxy clusters together, eventually isolating individual solar systems. At the terminal stage, the expansion of space becomes so violent that it overcomes atomic forces holding matter together, reducing planets to subatomic fragments. While the mathematics of the Big Rip are consistent, observations show no evidence that dark energy is increasing in strength, leading researchers to look elsewhere. The projection most consistent with current data is heat death, often called the Big Freeze. As the universe continues to expand at its current rate, galaxies will drift until they are light years beyond our observational reach. Eventually, the massive gas clouds that fuel new stellar birth will be exhausted, and existing stars will slowly burn out. This leads to a state of thermodynamic equilibrium, a cold environment fading into absolute darkness, where no energy remains to sustain physical activity. In this scenario, the universe reaches a quiet, eternal decay, where the physical processes we observe today simply cease to function. The Big Freeze is a projection based on the recorded movements of matter and energy across the cosmos. To map this, astrophysicists use the light from distant supernovae to calculate the precise speed of cosmic expansion over billions of years. These calculations are reinforced by temperature fluctuations in the cosmic microwave background, the oldest light in the universe. When we map the current distribution of galaxies over this ancient light, we see a consistent pattern of outward drift. Despite the consistency of these models, dark energy itself remains one of the least understood components of physics. Because cosmology is an evolving field, future measurements of how this energy behaves could still alter our understanding of the universe's final chapters. For now, the evidence points towards a cosmos that will eventually grow too thin and too cold to sustain the light of stars. While the final hours of the cosmos remain in the distant future, the data suggests we are already observing the mechanisms of its end.